Okay, so let's begin chapter 27 talking about circuits. And first, let's just say circuits are everywhere. Right? They're pretty ubiquitous in this day and age. They're in your phones, your computers, your tablets, your calculators, your TVs, your cars. Um, you know, pretty much everything besides like a standard old number two pencil has some kind of a circuit in it. And so, since circuits are so like ubiquitous in modern day life, it only makes sense that we get some kind of a familiarization with them throughout this course. And so, the first thing we want to keep in mind is that we can think of potential or voltage as a direct analogy to gravity, right, which we kind of discussed a bit. A potential difference is like a difference in height, right? If you carry something up to the top of a cliff, it has some gravitational potential energy. Just like if you move it to one side of a battery or another, it has some electric potential energy that's going to incentivize it to travel. And so, let's see. We should note that all circuits require moving charge. And whether that's a direct current or an alternating current, right, DC or AC, we'll get into those details a bit later. But important to note that every circuit requires charge to move in some way in order to function. Right? Charge is kind of the currency of a circuit. And so we've discussed that if there's moving charge, right, it probably experiences a force. And whether that's the Coulomb force, as an example, or more likely what we're going to have is F equals QE, right? And so there must be some kind of an E field, right? Because that's the language of charges, right? For it to know it should be experiencing a force, it must be in some kind of an electric field. And then we've also kind of discussed that electric fields come from potential differences or vice versa, right? You can say the electric field was there. It's a chicken egg scenario, kind of. Right? And so we get, at the end of the day, that we need some kind of a potential difference in order to move charge, right? That's the key idea here. And that's where potential and voltage as an analogy to gravity is going to kind of come into play. It's something you should be just keeping in the back of your mind as we go through this. Okay. And so we have this delta V, although the old-timey scientists came up with a nonsense phrase, which was electromotive force. Right. And it's because they kind of, saw if charges have to move, we all know F equals ma. And so if we're getting motion, right, and acceleration, there has to be some force at play. And so they just said, the battery is a force. Right. They didn't know all the details of what was going, on in there, but they just said, I don't know, batteries are full of force. They gave it their best shot. And so electromotive force is an outdated phrase, right? It's people still use it because it's conventional. It's what everyone's been using forever. But, just because something's been around a while doesn't necessarily mean it's good or correct. And so we have electromotive force, which could be EMF. It's also often just kind of like this swirly E. That's terrible. Well, I can do way better than that. That wasn't way better at all. But it's a swirly E. you get the idea. Okay, and so what we define for electromotive force is it is dW dQ, right? And which, as we're all familiar with, like the argument that, like, okay, if we have delta W, delta Q, and then we go, okay, you know what, why don't we take the limit of delta Q goes to 0, and we get the derivative out, right? We're all familiar with kind of this argument. Look at that, I'm getting good with the whatever. Right, and so it's the change in work per change in charge, right? And so, like, when we said that current I is equal to dq dt, it's the change in charge per change in time. And so this is the change in work per change in charge, right? Is what we're working with here as our loose definition for EMF. Okay. And so, right, if we have this, we can go ahead and say dq is equal to I dt. From here, we can say dW is equal to the EMF times dQ, right? So if we wanted, we could, integrate things to find stuff, right? And you can always do that when you have something like this set up. That should be something that kind of pops into your mind when you see this. But we're not going to go quite there yet. Okay, so this is a good start as to where we're trying to go. And I guess we should note that we're getting into chapter 27.4, and this is current in single loop circuit. Right, so we have an idea of where we're going, right? And so if we want, we can go ahead and plug in dq here, and we get dW is equal to E times I dt. Okay, and we'll kind of put this equation off to the side for a second. From last chapter, we had equation 26, 27, 6, whatever, that told us power is equal to I squared R, right? And that tells us that in a given time interval dt, an amount of energy I squared R dt will appear in a resistor as thermal energy. I'm going to say will dissipate. No, because we'll say appear. Dissipate would have been fine, I think. Okay. And so we said the amount of energy is going to be I squared R dt. And so what we can do is set that equal to dW, right? We're making more of like a logical argument here than actually following the math, which is usually a good thing, right? And so we can say EMF times dQ is equal to dW, which is going to be equal to I squared R dt. Okay. And so, meant to use this equation. So we have dq is equal to I dt, and then we can go, there's an I here, an I there, a dt here, a dt there. And so we can rewrite this as E is equal to IR. Right? Which should be strikingly similar, right? We had Ohm's law, which told us V is equal to IR. And we said the EMF is pretty much the same thing as V. I mean, there's slight nuances there, but in general, it's the same thing. And so we get Ohm's law out of this. So that's fun. And so, right, if we have some kind of a circuit we're going to look at, and we'll say we have, our battery, which we'll put a B next to just make sure we know that's a battery. And so that's going to come up, over, down. We have a resistor. Right, we can call the resistor R. Go plus sign, minus sign. And our EMF is going to be incentivizing charge to flow this way. Okay? And so that we can have some current I, which from conservation of charge and conservation of current, we know that current I is also flowing through the resistor in this, and then it also has to be flowing through here, and it goes back into the back of the battery, right? So everything's fine and good. And so what we could say is maybe some point here. Let me switch colors up a bit. Maybe some point here is at a higher potential, and then some point here is at a lower potential. And, just like when we had gravity problems, I don't want to say exercises, right? There's no problems. Right, in order to go from the high potential energy to the low potential energy, right, energy has to do something, right? And so for gravity, it was usually kinetic energy was what we transformed our potential energy into. Here it's heat, right? Resistors get hot when you flow current through them. And so this would be our P equals I squared R. And so the energy we dissipate through the resistor is kind of what mediates our drop to a lower potential, right? So instead of it being kinetic energy, it's heat, thermal energy. Okay. So we have that. That's all fine and good. And if we wanted to solve for the current in this circuit, we would just rearrange this and say I is equal to the EMF over R. Or, I is equal to V over R. But for this chapter, we'll stick with the E for EMF. And also, it's good to get used to different notations, because when you take, upper level classes or, go to grad school and you're reading papers or textbooks or whatever, different people will use different notations for things. And if you're unfamiliar with some, it's going to be a little harder then. Okay, and so the other way we can kind of tackle this is, I'm going crazy. That's not what I wanted to do. Well, okay, cool, that's the right color. Is if we wanted to, we could label this point at the circuit A. Okay. And we're going to say, well, we're not even going to give it a value. And we're just going to say at point A, we have a potential V sub A. Okay. And so if we're then going to go through this circuit, right, same direction as the current, make life easier. We head up here and we go, we start at VA, and then we go plus our EMF. We keep going. And then we discuss the current passing through the resistor is going to drop the energy. And we can write the drop in potential as V equals IR. And so we would say minus IR, right? Because that's our drop in potential. And then we keep going around, and we get back to VA. Right, so we're just kind of keeping track of the potential. We're using that as an accounting system. And so, right, if we look at this equation, we can cancel a VA on either side. And so we get E minus IR is equal to 0, which we can rewrite as E is equal to IR, or I is equal to EMF over R. All right, so there's just kind of two different ideas for how we can get to there, right? We got through this through conservation of energy, right? This argument here is conservation of energy. And here we just did a arguably much simpler line of reasoning, which is just following the potential. And so however you prefer to think about is perfectly okay. I think this method's a bit more elegant. And so there's a couple rules to this, right? We have our resistance rule. And moving through a resistor, in the direction of the current, changes the potential negative IR, right? Because we are dissipating thermal energy through the resistor, and so it's always going to be a lower potential if you go in the direction of the current. Period. In the opposite direction, the potential changes positive IR, right? Because if you're going the other way, you have to gain that potential back, right? Because you're starting at the state where the energy was dissipated, and then you're going back to where there's more energy. Okay? And then we also have the EMF rule, which is going to tell us moving through an ideal EMF, well, we'll say from the negative to the positive increases potential by plus whatever the EMF is, and then we can say opposite drops it minus A. All right, now that one's a bit more kind of clear. Okay. And so let's talk about internal resistance briefly. And this is just other single loops. And so we'll start with internal resistance. Right, and the idea here being that we don't always have an ideal EMF, and sometimes it has its own resistance. Right, like sometimes there is some amount of heat dissipated through the battery itself, which I feel like, if you've ever, I don't know, had a bunch of apps going on your phone at the same time and you can feel where the battery is gets really hot. That's what's happening here, right? You still have that P is equal to I squared R, going as heat dissipation through the internal resistance of the battery. I do think for the most part we use a lowercase r for this resistance, with the idea that like when it's a lowercase variable, it's kind of like intrinsic to a part of the circuit, right? And so this is inside the battery, it's intrinsic, so we keep it with lowercase. And so let's maybe, I'll just redraw that circuit. Right, and so what we did before was for an ideal EMF that has no internal resistance. And so now if we say there is some internal resistance, all we really do is, well, we just go we draw it as another resistor. And so where this one was capital R, this one's little r. Right, and so it's pretty much the exact same thing, only now we have to include the internal resistance. And so if we were again to start at some point A, should have been a lowercase a, just because that's the way, so we start out at some potential VA, and then we go up through our EMF, and then we go minus I lowercase r because we're going through this small resistor in the same direction the current's going. We get over to here where we go minus I capital R, and then we get back to VA. And then we can go ahead and say these VAs cancel. And so what are we trying to solve for? Current, of course. And so we can say E is equal to I times R plus R, or I is equal to E over R plus R. And so this is discharging a battery with an internal resistance. Okay. And then again, as long as you're careful to draw out your circuit, think about what direction current's going, and everything like that, you'll be fine. Single loops are relatively straightforward. But let's talk about resistors in series real quick. Okay, so what will we do if, let's say, we have our EMF, and golly gee, now there's 3 resistors. So we can call that one R1, there's R2, here's R3. Well, we know the EMF is going this way, and so we'll have some current I going this way, that way, this way, right? Conservation of current says that, you know, if there's no kind of a separate leg for it to escape off into, it's got to keep going. Right? Current's the flow of charge, right? Charges electrons, they got to be somewhere. I mean, here it's a conventional current, so we're thinking protons are flowing. But again, in reality, it is a bunch of negative charges going this way. We just stick with the conventional current, so we don't have as many minus signs. Okay, and then we can call this point B and this point A. And let's see, what do we want to do? We want to kind of rewrite this, just like we did with capacitors, as some equivalent circuit that's easier to take care of. So we have our EQ, we have our EMF, keep some point B, some point A, right? Just like we had all the resistors between B and A, now we have the equivalent resistance between B and A as well. And we have some current I going down through here. And so this is our goal. Right, because as you can imagine, it's a lot easier to deal with the equivalent circuit than it is like the actual circuit. And so, let's see. If we want, we can, let's see, I guess we'll start at our point A. We're going to do something similar, where we'll start at VA, and then we go up through here, and so we have plus our EMF, and then we have minus IR1 as we go through this resistor, and then minus IR2, minus IR3, and we get that's equal to the potential at some point A as well, right? We're ignoring B because it's irrelevant here, right? And then we get the A's cancel out, and so that goes away as well. And so we get our EMF is equal to, well, let's see, these are all being multiplied by I, and it's negative, so we'll move it over. And so we can say I times R1 plus R2 plus R3, right? And we'll star that equation for now. And now let's look at the equivalent circuit, right? And we'll do the same thing. Start out at VA, and then we go up here, so we go plus E, and then we go down through here, so minus IREQ, and we're back to our starting potential. We can go ahead and cancel these out. We can move this to the other side, and we get the EMF is equal to REQ. And we'll double star that one. And so if we look at these two equations, right, we have E is equal to I, E is equal to I, and then we have this as REQ. And so we can go ahead and make the argument that REQ is the sum of the individual resistances. And that's 4 resistors in series. Okay. So we had that for, I guess, I'll go ahead and make it for N resistors in series, right? And so you can go up to however many resistors you want. As long as they're in series, you add the resistances together, and you find the equivalent resistance, which we saw that in lab. Okay. So that's all fine and good. Okay, so now if we wanted to find the potential difference between 2 points in a circuit. Let's start drawing out the circuit. And so we're going to have a EMF with an internal resistance. And I guess we're going to go ahead and just kind of block this off as being the battery. Anyway. Right, and just kind of say like, hey, this is the battery, has an internal resistance, so we're gonna go ahead and just mark that as what it is. And then let's just say we have one resistor outside of the battery, and we can say that's equal to 4 ohms. We can say little r. All right, let me change the colors up a bit just so we're not. Little r is equal to 2 ohms. We'll say our EMF is 12 volts. Right, we'll kind of note that the EMF is going this way. I don't like that it's in there twice. So we'll note the EMF goes up. And then just like we always have, we'll have a current I that goes through there, comes back down through here. If we want, we can also draw it going through this leg. Right, and that's just, current's the flow of charge. Charge is conserved. If there's not some kind of weird little offshoot for it to take, it has to stay in that leg of the circuit. And so then what we can also do is label the negative side of the battery. We'll call that A, and it's negative. And then we'll go to the positive side of the battery and have that B, it's positive. Right, for the whole battery. So we have plus and minus for just the potential of the battery, but then there's also the EMF of the battery, and then there's the total potential. Okay, so simmer down. Okay, and so if we kind of go through our accounting of potentials starting at VA, we have VA, then we go through the battery, so plus our EMF, we're going with the current through that little resistor, the internal resistance, so we go minus I, lowercase r, and then we get to VB, right? And then if we wanted to look at like the actual circuit itself, we could start at VB, go up, through, down, around, and the only really thing we interact with is the resistor, and so we would go minus IR, and that's going to be equal to VA. I guess these should be lowercase b's if we're going to be just good people. Okay. And so we have this, and if we want, we could maybe move the VA over here to get VB minus VA is E minus IR. And then here we can bring VA over here, and we get VB minus VA is, we're going to bring that over there, is equal to IR. Okay, so I feel like we're off to a pretty good start already. We have the equation from before right here. And so if we have, I'll write that off to the side real quick. For an internal battery, I is equal to, or an internal resistance of a battery, I is equal to the EMF plus the resistance of the circuit plus the resistance of the battery. Okay. And so we can plug that in here, and we get VB minus VA is equal to the EMF minus I, which is all of this, EMF over R plus R times little r. Okay. And then we can also since that's the current going through the battery, it has to be the current going through the circuit. So we can go ahead and plug that in for here too. And so we have VB minus VA is equal to epsilon over R plus R, and then times big R. Okay. And let's see. Yeah, I guess if we're looking for the potential difference, we can kind of solve either of these, right? This one looks a little easier. So we'll go VB minus VA is equal to epsilon, 12 volts, over R plus R, so that's going to be 2 plus 4, well, we'll just write it out. And then times big R, which we had as 4 ohms. And so let's see, we get, well, up top we can get a 48, and we'll call that volt ohms. And then on the bottom we have 6 ohms. All right, go ahead and say these ohms cancel out, makes our life good. And we get VB minus VA is equal to 8. All right, 48 divided by 6 gives us 8 volts. Okay. And so that's fun. And so we can also see that the potential difference across this battery with an internal resistance directly depended on what else was happening in the circuit, because the current also depends on that. And so if we were to take the exact same battery, right, that we kind of boxed out in white, and wire it up to a different circuit, we would get a different potential difference across the battery. And so that's interesting to note. Yeah. So let's talk about grounding a circuit very briefly. All right, so let's think back to what we did with some gravity problems and potential energy. We had a lot going on where we would, maybe have a cliff, you got a box on the cliff, and then we would always go through and say, hey, where does y equal 0 at? Right? That was always useful for figuring out where the potential energy is 0. We do the exact same thing with circuits, only we call it grounding, which this is also the ground. Haha. That was dumb. All right. And so if we have the same circuit we had before, we'll go ahead and do here, this is all the battery, boo. So we had R is equal to 4 ohms, little r, 2 ohms. The EMF is going up. It's equal to 12 volts. We went ahead and said we had some point A, which was negative, B was positive, and we had our current I that flows through. Right, so just the exact same setup as we just dealt with. And then what I'm going to do, copy, no, paste, sick. Okay, and so we're going to have these two circuits kind of next to each other. And then I'm going to ground each of these this one will ground down here, and this one will ground up here. All right, and that's the kind of the symbol for ground. And we'll note the ground is chosen to be the 0 of potential. Okay. And so, let's see. And so now if we go through all these same arguments, we'll start with this circuit, and we have VA, right? That's chosen to be the ground. And so we have 0 plus E minus IR. I think we can get away with just saying is equal to VB. Whereas here we're going to say VA plus E minus IR is now equal to 0 because we're grounded there. Okay. And so I'm not going to go through, all the argument, but the idea here is we chose here VA is equal to 0 and VB is equal to the 8 volts, right? We know the potential difference between A and B is 8 volts. And so we don't have to really go through and rediscover that. And so this is what we get as our result here. Over here, though, we get VB was 0. And so that means VA has to be negative 8 volts, right? We're going in the positive direction and we get to 0. And so this is what we get over here. And none of the physics changes, right? You have the same potential difference from VA to VB, or VB to VA, however you want to phrase it. But it's just interesting to note that by grounding it, you can change the individual potentials, but delta V is equal to 8 volts regardless. Okay? And so that's the idea of grounding. And in some circuits, it'll save you a lot of time instead of having to go through like all this rigmarole of like, oh, we got to move the VA over here to figure, like, it's just one of them 0. It makes life a little easier. Okay. The next section's kind of redundant, so let's go right into multi-loop circuits and have that be 27.7. Multi-loop circuits. And so this is going to be a fun one. Sorry about that. Knock on the door, but I'm back. And so for multi-loop circuits, let's go ahead and draw out a circuit. Okay, and so we have E1 going this way, EMF2 going this way, R1, R2, R3, and I think we call this A, that's B, there's C, and I'll come to some point D, I1. And so now we can't say the current's going to be the same everywhere because it has junctions where it can split off. And so we're going to just kind of guess some directions. We'll say I3 is going down, and then probably means I2 is going up. And we'll mess around with this and see what's going on. And so first, let's look at D. And let's see what's going on in there. So we have D, and we have 3 wires. If we were to continue the direction of I1, we'll see I1's going into D, I2's going out, and then I3 is going in. And so that tells us I1 plus I3 is equal to I2, right? And so that's the junction rule. The sum of the currents entering any junction must be equal to the sum of currents leaving that junction. Right, and we kind of discussed this when we first introduced current and charge and all of that. And this is, again, just a statement of conservation of current, conservation of charge. This is often called Kirchhoff's junction rule, or sometimes called his current law. Yeah, and it's so we'll probably just call it the junction rule for simplicity, but you can also talk about it as Kirchhoff's. Okay. And so that's that part. And so we have, what do we have? One equation, 3 unknowns. Not a great start, right? Okay, start that. That's going to come back into play in a second. And so what we can do is look at the individual loops, okay? And so let's say we're going to start at, get rid of this. I guess we'll switch the colors up a bit just to not make it too messy. And let's see. And so if we start at point B and we're going to travel in a loop that goes this way. Okay. And so I know before we would start at VB, end at VB, cancel them out. We're gonna kind of skip that part for right now. Let me see. I wonder, can I? Goodbye, Kirchhoff. And so if we go, let's see, we're starting at our point B. And so the first thing we have is E1. Then we go around the corner here, and we go minus I1, R1. We keep going till we go up here. Now we're going in the opposite direction of the current, right? And so we need to go to a higher energy, right? Because we're undoing that dissipation of thermal energy. I mean, mathematically, we're not really undoing anything. And so we have plus I3, R3, and we're back to VB, so we can say is equal to 0, right? And so, the same thing we did before where we would say, oh, VB plus is equal to VB, cancel them out, yada, yada, yada. We're just going straight to the goal. Okay, and so we have one other equation now. We'll call this equation 2. I'll go ahead and rewrite equation 1 over here just so we have them all together. And might as well keep changing the colors up. Why not? And so let's see. Now let's start again at point B, I guess. And we're going to go this way. And so let's see. First we have minus I3R3, right? Because we're going straight down through here as our first step. And then we're going with I1 through R2. And so we're also going to have minus I2 R2. And then we're going the opposite direction of E2. So we'll have minus E2, and we're back to B is equal to 0. Okay. And then if we want to get real fancy, funky, fresh, we could go in one big loop around here, which we'll do that, and then we'll see how that's kind of redundant. And so we have E1 minus I1 R1, zoop, 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 and then we have minus I2 R2 because we're over here, and then minus E2 is equal to 0. Okay. And that's just the sum of these two equations, right? We have E1, E1, minus I1, R1, minus I1, R1. We have plus I3, R3, minus I3, R3. So that goes away. And then we have the minus I2, R2, minus E2 equal to 0. And so that's kind of a redundant equation. Okay. And so now what we can do is, if we want, I think in the interest of time, I'm not going to go through all that algebra right now, but, plug in I2 is equal to I1 plus I3, wherever we can. And so we plug that in there, maybe solve this whole thing for I3, and then plug that into here, and then we can solve for I1, if we knew the E's and the R's, right? Or if maybe we were given a current and we're missing some E's and R's, right? It always works out to be you have the same amount of equations as unknowns. And so in this one, we would have to be given E1, E2, R1, R2, R3. And then we can use these three equations here, right? Because this one's kind of redundant. And we have 3 equations, 3 unknowns. Cool. And so let's hop into resistors in parallel. Okay. And we will go. Have some battery. I'm gonna give ourselves a bit more space. R1, R2, R3. We have our batteries going this way. All right, and again, we're going to just say this is an ideal battery. And what our goal is to rewrite this. As some R equivalent. All right, and so let's see. We're going to have current going through here. We can call this I. We can call this I1. We'll call this I2. And we'll call this I3. Well, if this is I1 and that's I2, then and this is I3, then what goes through this leg has to be the sum of I2 and I3. And so we'll call this I2 plus I3. And then right here we just have I3. Down here it's also just I3. Here again, right, we have I2 and I3 coming in. So I2 plus I3. And this is overkill, right? We don't need to do all of this. Right? In reality, like, a little sanity check to go through and say, yeah, this all makes sense. But, right, that was a lot. Probably get rid of that one too. Right. And so, right, our equivalent circuit, plus minus, and we just want some current I going through it. If we want, we can also have our point A and point B, kind of like where we're just going to be doing, checks. And then it's also like, right, A and B is across the battery, and then the whole other circuit's on one side. A, B is going across the battery, whole other circuit on one side. All right, so it just kind of helps to make sure your equivalent circuit is equivalent, but it's not entirely necessary. And so, let's start at point B and just go through the left loop. And we get, what do we get? Let me just make sure that's how I want to do this. Oh, and well, so before we even get into that, right, so if this is, an ideal conductor, right, there's no potential difference in a conductor, right, it's all equipotential. So then all of this is all at VA. And then we could say all of this is all at VB. Okay? And so what that tells us is if we were to go through and have some delta V1, delta V2, delta V3, E is equal to delta V1 is equal to delta V2 is equal to delta V3. Versus where when we had resistors in series, right, you could find some delta V1, delta V2, delta V3 that all depend on the individual resistances, right? So you would have delta V1 is equal to IR1, delta V2 is equal to IR2, that's a 1, and delta V3 is equal to IR3. And the currents are the same because it's in series, but the potentials aren't. And so, right, for resistors in series, same current. Resistors in parallel, same potential, is what we want to kind of keep in mind. Okay. And so what we can go ahead and do and say I1 is equal to, well, if we had V equals IR, then I equals V over R. And we said these are all going to be, we can just call it V. So we can say V over R1. And then we can say I2 is equal to V over R2. And I3 is equal to V over R3. Okay. And then, I don't know, if we look at, where do we want to look? At this junction here, we can say I is equal to I1 plus I2 plus I3. Next we have I1, then I2 plus I3. And we can go ahead and substitute these in. Okay. And so we have I is equal to, all right, I1 plus I2 plus I3, which is going to be V over R1 plus V over R2 plus V over R3. I'm going to factor out a V and then make that 1 over R1 plus 1 over R2 plus 1 over R3. Okay. And so we have this equation here. Cool. And now let's take a look at our equivalent circuit. So let's say we have, our same potential V, right? Or, EMF, however you want to look at it. Right? Maybe the EMF has an internal resistance. And so when you get those together, you find the total potential V. And so, we'll keep it as V. And so for this, we just have I is equal to V over R EQ, right? We took V equals IR, and we just rearranged it for this circuit. Okay, and so we know the I and the V's are the same. That looked weird. And so what we can write is 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? Because if the I and the V are the same, then this and this must be the same. Well, I guess the 1 over that must be the same. Cool. Okay. And so that's often written as 1 over REQ is equal to the sum of J equals 1 to N of 1 over R sub J. I prefer writing it as REQ is equal to that. Right, because it gets to the thing we're looking for. Super important to note that you can't just flip all of these and add them together, right? Like this to the -1 is not equal to just R1 plus R2 plus R3. All right, that's a really common mistake that we're not going to make. None of it is, it's a learning opportunity. And so it's also a good little equation to have. Well, I guess we'll go ahead and say this is N resistors in parallel. It's a terrible N. There we go. And if we have 2 resistors, then REQ is equal to R1, R2 over R1 plus R2. And you can manipulate this equation for 2 resistors and see that that's true. Well, might as well just go ahead and do that real quick. So if we have 1 over R1 plus 1 over R2 to the -1, we want to make common denominators. So we'll multiply this by R2 over R2, and this one by R1 over R1, and we get R2 over R1, R2, plus R1 over R1, R2 to the -1 gives us R1 plus R2 over R1, R2 to the -1, which gives us that. Cool. And let's see. We will go ahead and call it a day there. But I am going to post like a supplemental video on RC circuits.